Okay, so we're looking at section 2.1, and on the previous page we looked at grouping a discrete data set, and now I want to show you how it's different if the data that we're grouping is continuous. So if we're grouping continuous data, then it's common to use the symbol through followed by a less than rather than the through symbol by itself, and we're going to read this as through less than. So just through followed by less than, just like it looks. And there's two main reasons we're going to do this. One of them is to avoid any gaps, and the other is to produce a more accurate midpoint. So the thing with gaps is if you have a gap between, like, say 9 and 10, like on our last example, and there's no possibility of data taking on a value like 9.7, then that gap is not a problem. But if your data is continuous, then anytime you have a gap, there's a possibility that data would fall there. So with continuous data, we need to avoid gaps. And then I'll discuss the issue of midpoint as we go through this example. So let's go ahead and jump in and take a look. In this example, we're looking at the duration of labor in hours for a random sample of 28 pregnant women during natural childbirth. That was recorded and shown in the table below. And we want to create a group data table for the data set beginning with the class 0 through less than 5. So that's our starting point, 0 through less than 5. And so the next class, there might be some temptation to start it at 6, but this is 0 through things that are smaller than 5, so that would include 4, 4.9, 4.99, 4.99999, but it does not include the 5. So we need a spot for the 5, so that would be the beginning of our next class. And then we want that to be consistent, and from 0 to 5 you would add 5, so I would do that here and add 5 to the 5 and get a 10. And it looks like my next class should be 5 through less than 10, and that would be consistent with the one that I had before. Now usually when I go to fill these in, instead of working left to right, once I kind of see that it's a plus 5, I just work down vertically. So I have 0, 5, 10, 15, 20, 25, and 30. And I would do that on the other side as well, just keep adding the 5. So I'd have 15, 20, 25, 30, and then finally a 35 there at the bottom. We never have a total for our class description, so I would just go ahead and shade that in to show that that's not necessary. And once we've done that, we're basically set up to do the same thing we did on the previous page now. We just have to be kind of clear on this. If the value, say 15 exactly should show up, does it go on this line or this line? So this is 10 through less than 15, so that's things like 14.9, 14.999, but not 15. So if you happen to land right on that boundary, that goes on this class that starts at 15, not there. So that typically wouldn't happen, but it is good to know what to do in case it does. So a lot of this table's already been filled in. This was really the main thing that I wanted you to see that's different. So let me just go ahead and fill in these frequencies, hunting for any labor durations that were in the 5 to 10 hour range. And I'll cross them off as I go along. So I see 1, 2, 3, 4, 5, 6, 7. So I'm coming up with 7 right there. I always want to do kind of a quick scan to see if I missed anything, and I don't notice anything at the moment. If I did, there'll be a chance to catch that later. And then the other ones are done, so I'll go ahead and drop down to look for all the labors that are in the lower 20s. So there's 1, 2, 3, and 4, and 5. And I'm just going to do a quick look to see if I missed any others in the lower 20s. I don't see any, so it looks like that would be a 5. And then the way that I would double check this, if I was doing the whole table, I'd just make sure everything was crossed off. But since some of it's been filled in already, I'm just going to look at this total and make sure it matches the number of women in the sample. So I have 8 here, plus 4 is 12, plus another 9 would be 21. And then it looks like we have 7 more here to add to that 21, which would put us at 28. And if we were to look back up at the original problem, it says it was a sample of 28 women. So it doesn't look like anything was missed, so that's a good sign. So that takes care of the frequency. That's just like the previous section. And then we'd want to turn those into relative frequencies, and we're going to do that in the same way. We would take every frequency and divide by the total of the frequency column, and then put the decimal here to 4 places to match the other ones. So let's go ahead and bring the calculator in here and do those calculations. Let me slide this over so we can see it all. So let's just scoot that a little bit more. So if I did 7 divided by, let me clear out that other stuff, 7 divided by 28, I get 0.25. That's exact, and if I stop there, it doesn't cause any error in the number, but I do want it to look consistent with the others, so I would add the 2 zeros onto that to be consistent. And then the next one that we have missing is for this frequency of 5, so 5 divided by 28 is 0.178, and then it's a 5, but followed by a 7, so I'd round that up to be a 6. And then these are relative frequencies, so just like on the last problem, they should add up to 1, possibly off a tiny bit if there's some rounding error. So I'll just go ahead and add those up real quick. And I get 1. And even though the calculator just says 1, I added up numbers that had 4 decimal places. So I'm going to write 1.0000 and be consistent with that 4 decimal places all the way down. And then the other thing that we have missing on our chart still would be the midpoints. And I usually do those in my head, what's halfway between 5 and 10, what's right in the middle of 5 and 10, and that would be 7.5, and what's right halfway in the middle between 20 through less than 25, that would be 22.5. And that seems consistent with the other ones that were given that seem to be apart by 5, and that fits right in that pattern. If you're having a hard time doing those midpoints in your head when they come out to be a decimal, you can use the math definition on that and say that if my class goes from 5 to 10, then I would want to do 5 plus 10 divided by 2, and that would give you the 7.5 as well. So that's not necessary to use the calculator if the numbers are nice enough, but if you feel more comfortable doing the calculation, definitely feel free. Alright, and on midpoints we would never put a total either, so I'll go ahead and just shade that one in. And then just a quick comment there. The avoiding gaps, again with continuous data, if there's a gap we might have data that would fall in there, and that's a problem. We avoided gaps by having our upper cut point match our next lower cut point. And the idea of midpoints is if you were to look on a number line between 5 and 10 and think just measuring what's halfway between 5 and 10, it would be 7.5. But if this was really discrete data and whole numbers, then the biggest number that would go in there was 9. And if you looked at a list that was 5, 6, 7, 8, 9, then the middle would be a 7, not a 7.5. So that midpoint really is different between a discrete data set and a continuous one, and making sure we show the proper upper cut point for what's possible helps us to get the right midpoint. So it is important that we use a different symbol for the discrete versus the continuous if we want all that to work out well. And then just following up, if we're going to do grouping of data, it should be to help us see some patterns. And so they're trying to get at that a little by asking us a question, so we'll start out with that and then see if there's other patterns we can spot. So what percentage of women had labor that lasted less than 20 hours? So that would be any women in these top 4 classes. So I'll draw a line right there that separates the women whose labor was 20 and below from those that were 20 and above. Actually below 20, because 20 is not included there. And that's good because this says strictly less than, so we don't want the 20 to be counted. But all of these we want. And it looks like we have the 1 plus 7 is 8, plus 4 is 12, plus the 9 is 21. So there would be 21 women out of 28. If we divide that on the calculator, we get 0.75, and that would be 75%. So that would be the answer to their question. And when I did this in class most recently, I had a student ask me, well, why didn't you just add up these? These are already in decimal form. Why would you have to do the division over again? And there's 2 answers that I gave to that. One of them is it's actually easier for me to add up these whole numbers and divide by 28. I did that in my head, but if I'm doing these, I'm going to turn to the calculator. It's a much harder addition. And then the other reason is these numbers aren't rounded, and these have been. And I would rather go with numbers that were exact than numbers that had rounding error and just save any rounding for the very end of the process instead of having it occur in the middle. And then the other thing that's worth a note before we go on is just looking to see if there's any other patterns that we can see. I would often look for peaks. And when I look at the frequency, the highest frequencies kind of represent those most common things. And I have kind of a couple high spots there at 7 and 9. And so when I see that, I might start thinking, well, why is that? How come there's 2 different spots that are common, this 5 to 10 zone and also that 15 to 20 zone? And I don't know for sure, but once I see that pattern, I can start speculating. And one of the things that I might think is maybe these were first-time births for the mothers, and those often end up being a longer labor, and then maybe this was a second, third, or fourth birth for that mother, which sometimes can be faster. And so you might have the two peaks representing first time deliveries for those mothers and second, third, fourth time deliveries for those mothers. So that's a possibility. But I think that's something I wouldn't have even noticed if I had just looked at the data, but once it's grouped, I start to see that. Alright, so on this problem that we just finished and on the one on the previous page, on both of those they told us the starting class, and when that happens it makes it easier for us to set up the rest of them. And that is really common in a textbook situation, but in a real life situation you're going to collect that data and it's going to be up to you to decide what the first class is, and then that sets the standard for the rest of the way. So I do have some guidelines here that you could look at, and that would help you in a real life case where you're making those decisions. Again, in most of the ones that you're going to do in the book, they'll set the first class for you, but I do want you to know how to handle it if they don't. So the guidelines are the number of classes should be somewhere between 5 and 20, and I would even say that you might want to keep that max more like close to 10 for small data sets. If it was a large data set, say instead of 28 women like we had in this problem, it was 280 or 2,800 women, then to spread that out over 20 classes is still condensing it down to quite a lot less for someone to look at. But if you start out with 28 women and you have 20 classes, you're really not making that easier for people to process. So for small data sets like we have in most of the homework, we usually like to do between 5 and 10 classes. But real life data often is a large data set, and then more classes would be reasonable. And we want at least 5 so that you can see patterns. If you don't have enough classes, it's hard for patterns to emerge. And we try to keep it below 20 because we're grouping, because raw data can be overwhelming, but a table with too many classes can be overwhelming as well, so we're trying to avoid that problem. And then each piece of data should fit into exactly one class. That makes sure that we end at 5 and start again at 5 when it's continuous, so that there's a place for everything. And it also has to do with this, should we use through or through less than, where we're really thinking about discrete versus continuous, because if we fail to consider that, we might not even have a place for things to go at all. So thinking about continuous versus discrete is important on that line. When it's possible, classes should all be the same width. And again, when I lectured on this last, I actually told people, it's technically always possible to use the same width, but that might cause you to violate this or to have some kind of terrible grouping. So it's maybe smarter to say when practical, the classes should all be the same width. When you ask kids, you give them a wide glass of soda and a tall skinny glass of soda, and you pour the same amount of soda into each one and ask them which glass they pick, they'll usually pick the tall skinny one because they go just by height. I would say when we're thinking about this grouping, the frequency represents height. And in order for us to really think like, okay, this 9 is about twice as big as the 4, that only makes sense if the size of our glass, if you will, is the same, so we do want to try and have an equal width there. One reason it might not be practical to do this is if you had an outlier. Let's say you were grouping income and you happen to have Bill Gates in your class brushing up on his statistics, and he has his income of, I don't know, say $7 billion a year. It's hard to use a width that is practical for most people in the class and then still get to Bill within 5 to 20. So sometimes when you have a severe outlier, you'll think about what should the classes be for most of my data, and then you might have a category at the end that is like $100,000 and more or $1 million and over, something like that to catch your outliers. So that's not real common, but you'll see that from time to time. And then a couple other things to note. The lower cut points should be nice numbers if possible. So I like that we used a width of 5 here. It was easy to count, 0, 5, 10, 15, 20. But if we had started a messy number, like 2.7 or something, then it's still hard to count up in 5. So if you want to pick a nice number for your scale or your width, you also want to have a nice number for your first cut point, so you're starting at a good place. And we never want to begin or end with an empty class. We're saying up there that we want 5 classes, and sometimes we get into a situation where we only have 4, and someone says, oh, I can fix that, I'll just throw in another one. But if there's no data that goes into that, you really should redo your classes so that they're narrower, have a smaller width, and you end up with more classes. If you do have an empty in the middle, that's fine. In fact, that's important because it helps show that some data values are kind of standing off on their own. So It's not a problem to have an empty class in your chart, but you don't want it to be the first class or the last class. Alright, continuing on in section 1.2, I want to show you one more example with quantitative data, and we've already seen an example of both continuous and discrete, but it turns out something different happens with this one, so I want you to see an example of that before you head off to homework. So let's jump in, we'll see what's different about this one. So the following are the scores on a homework assignment for 44 students, and they want us to construct a group data table for the data. And it looks like these are whole numbers here, and this is actually homework assignments from a chapter 1 homework from one of my past classes. And so I'll just give you insight into my grading here. I only use whole numbers. I never give somebody like a 3.7, a 4.2. If it's a 4.2, I round it down to a 4. If it's a 4.7, I round it up to a 5. So not only do you see whole numbers here, but the way I grade it, that's all that's going to be possible. So I would argue then this is a discrete data set, and I would start thinking then, okay, so I'm going to use the through symbol. What should my first class be? And you look at the scores, and the smallest number you see anywhere is a 0. So you think, all right, my starting point should be 0, and that's correct. But there's something a little tricky to that, so I'm going to show you that off to the side, and we'll fill in the correct answer here in a minute. You can just watch this instead of writing it down, but what if I were to start with 0 and go 0 through? What would I go to? Last time I asked students this in class, they said go with a 1. And if I do that, then I think, all right, so what's the next class? And it can't be a 1 because with the through symbol, which we would use for discrete, 1 is included on this class. We don't want it included on both classes. So we'd go up to 2, and that would make this one 2 through 3. And following that pattern, the next one would be 4 through 5. But if you do that, you only get 3 classes. And again, you can't just add 6 through 7, 8 through 9, and have blank classes, empty classes at the end. So you have to somehow make these classes smaller. Well, only 2 numbers fit here right now, 0 and 1. If you made it smaller, so I'll go ahead and cross this try off. Another try might be, well, how about 0 through something smaller? Well, the next number smaller than 1 is 0. And this, in a way, is actually what we're going to do, is say our first class is 0 through 0, our next class is 1 through 2, and 2 through 2, and so on. But it's kind of silly to list a range when there's only one number that goes in there. So for 0 through 0, what we would do is just list a 0, just that one number. And for the 1 through 1, we'd put the 1, and the same for the 2, and also the 3, the 4, and the 5. So this is referred to as single value grouping, where what we're doing is saying, look, we're just going to let every different value be its own class. And that works out okay because we get 6 classes, which is in that 5 to 20 range. From there, the rest of this is pretty similar to what we did on the last couple, so I'll just try and go through this quickly and then check for mistakes at the end. But I want to count my zeros, so 1, 2, 3 of those. I want to count my ones, 1, 2, only 2 of those. I want to count the 2s, so 1, 2, 3 of those. And then the 3s, 1, 2, 3, 4, 5, 6, 7, 8, 9 of those. And then the 4s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of those. And for the 5s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of those. And I think I have them all. A little swervy, but I think I have them all. And the way I would double check that is to add them up. So I have 5 plus 3 is 8, plus 9 would be, 17, plus the 16 would be 33, plus the 11 would be 44. So that's the right total. So I think I've got everything. Alright, so we're finished with those frequencies. Now we want to move on to the relative frequencies. And that means we're just going to divide each one of these by 44. So let me see, go ahead and move this over, I guess, so we can see the calculator and the paper at the same time. Clear out that old stuff. So I have 3 over 44, 0.0682. Notice it is actually a 1, but we want to round that up because of the 8. 2 over 44, 0.045, and then after that it's a 4, but followed by a 5, so we'll round up. That'll be a 5. The 3 over 44, of course, will come out the same as it did last time, so just copy that again. And then 9 out of 44, is 2045. That one does not get rounded up because it was followed by a 4. 16 out of 44, 0.3636. And finally 11 out of 44, which comes out 0.25. But like I mentioned on the last one, if you've been rounding to 4 all along on the others, be consistent and show that on the exact ones as well by adding the extra zeros. I'll add all these up real quick to make sure I'm getting the right total, which for relative frequency we always expect a 1, though rounding error can throw that off a little. And I do get a 1 exactly, so the rounding error is balancing out, but I will still not list a 1. I'll list a 1 with 4 zeros because I really did add up all those decimals and I want people to see it didn't end up a little bit off. It did all balance out. A lot of these were rounded and do have error, but apparently the error is balancing. And then when we go to do the midpoint, what we want to remember is, like, why do we do a midpoint? And it's so that we have a representative for a range of values. And here if I say, okay, there were 16 people in this class, what was their homework score? We just look and we say it was a 4. It's not like it was a range that said 4 through 8 and we have to guess. So if we were to even put a midpoint, it would just be this number again. So we don't bother with a midpoint when we do single value grouping. And we can go ahead and fill those notes in. We'll come back and answer this other question. If for single value grouping, which is what this table is, each class consists of just a single possible value, so you just list what that value is instead of using a range. And when you do this type, no midpoint is needed. If you went back and looked at the definition of a group data table, it says it includes a midpoint if it's appropriate, but here there's no need for it, so it's not appropriate. And then just looking at the last question, based on this first assignment, does it look like a majority of the students are on their way to being eligible for test corrections? So you may or may not remember this from the syllabus, but I said that if you average 3.5 points or higher on your homework, that would earn you a test correction for your homework efforts. And so after only one assignment, Chapter 1, you'd have to have a 4 or a 5 on that, so the break is right here for that. And how many of the students have met that? So you have to get a 4 or a 5 to be on your way for being eligible for test corrections. And we have 16 plus 11 that are eligible. And then I want to think of that as a fraction, so out of 44. And so that's 27 out of 44. And I'll go to a decimal on that on the calculator. Just do that off to the side. I get 0.6136. And they didn't actually ask for a percentage. They asked, what did they say here? Does it look like a majority? So a majority is greater than 50% or greater than 0.5. This is greater than 0.5. And that implies that the answer to this question would be yes, it does look like a majority of the students are on their way to being eligible for test corrections. And I will just remind you of something in case you didn't get a 4 or 5 on Chapter 1. If you got a 2 or a 3, it doesn't mean you're not going to be eligible for test corrections, but you have to average 3.5, so you'll have to make it up. So if you got a 3 and you get a 4 somewhere else, those will average out. If you got a 2 and you get a 5 to balance it, you'll still average out and be okay. So hope is not lost yet, but it is good to be off to a good start already. And just another look at these in case you missed them as I slid them down. So there's our one note there. Single value grouping consists of a single possible value for each group, and our other note that no midpoint is needed for this type. Okay, we're going to go ahead and finish up section 2.1 here. We've already looked at grouping data that was quantitative. We did that for both continuous, discrete, and single value grouping. And now we're going to look at how things are different if it's categorical data. So let's look at an example. As of 1998, the all-time top television programs by rating, which is the percentage of TV-owning households tuned into the program, are as shown in the following table. And the table here lists the program name and then the network that carried that and then the percentage of people who watched that show. When we look down here at our directions, we see that they want us to construct a grouped data table for the network data. So that's going to be this column here with the CBS, ABC, NBC, and so on. And that's categorical, so that's what's going to cause us to do things slightly different. So when we're doing categorical data, for our classes we just list the different possibilities that variable can take on. In this case the networks are ABC, CBS, or NBC. Doesn't really matter too much what order you put those in, so I just went ahead and did them alphabetically. And then for the frequency, we just go count up how many times each of those occurred. So let me pull this down here and let's look for the ABCs. So 1, 2, 3, 4, looks like 5 of those. So I'll fill that frequency into my chart on the ABC line. And then I'd want to do the same thing for CBS. So we go through looking for those. There's 1, 2, 3, 4, 5, 6, 7, 8 of those. So I can go ahead and fill that in now. I'm using different colors here just to help that show up on the video, but of course that's not necessary for you to do when you're doing your homework or quizzes or assignments. And then finally the NBC, we'll go look for those. So let's see, we have 1, 2, 3, 4, 5, 6, and 7 of those, and then I'll fill that in. And one of the things you would want to do is to add that total. So the 5 plus 8 is 13, plus the 7 is 20, and that matches with the total that we were given. So that kind of confirms that we didn't miss anything. The next thing to add to this chart would be relative frequencies. Those are done just like they were before. So I'm going to take each one of these frequencies and I'm going to divide that by the total frequency of 20. And I'll just do that on the side on my calculator. When I do 5 over 20, I get 0.25, so I'll fill that in. When I do 8 over 20 on the calculator, I actually get 0.4. But because I've put 2 decimals on the one above, I want to be consistent, so I'm going to put 0.40 for that one. And then for the final one, I have 7 over 20, and that one comes out to be 0.35. Now you should go ahead and total these and make sure that they total up to the expected 1, which they do in this case. And you should also be consistent with your decimals. So since you use 2 places here and here, you should go ahead and use 2 in the total as well. You might remember from the previous pages that we said if you're going to round your relative frequencies, you should put at least 4 decimal places. And so that might seem like an error here that I've only done 2. But in fact, I didn't need to round these. These are exact. So when you have exact relative frequencies, it's okay if they're shorter, but you still want to have that consistency all down the column. And then finally, the midpoint's job is to serve as a representative for a class when there's a range of different values that can fall in there. So that really only applies to to quantitative data. We don't apply that to categorical. So we can just go ahead and remove that column, and when you're doing homework or a test or quiz, you could just leave that midpoint column off whenever it's categorical. And we'll just make a note of that right here. No midpoint is needed in the table if you're doing categorical data. All right, that concludes section 2.1.